Well, it's a well-known fact that cats have 7 lives, and those cats would be very envious of Harold Whittam today. Almost half a century of mathematical activity, and what a variety of profound achievements. After spending his early years at Stuyvesant in Manhattan, I believe that Harold Whittam and Richard Feynman were classmates. And then at the City College of New York at the University of Chicago, he wrote his thesis on Neumann algebras with Professor Irving Kaplansky. He spent a decade or so at Cornell, where he tackled a wide spectrum of problems on integral equations, Wiener-Hopf types of problems, Toeplitz matrices and operators, stable Markov processes. Mark Katz jokingly once said that he had been able to convert Harold Whittam to looking at real mathematical problems. After Cornell, with in his bag NSF fellowship, Sloan's and Guggenheim's, he then moved in the late 60s to sunnier climates, where he engaged in the hard analytical questions on Toeplitz determinants, block Toeplitz determinants, etc., all the problems that we love and use. In the next life, around his promotion to emeritus professor, he embarked, together with Craig Tracy, into a new field, the field which brought us together today at MSRI. After the major discoveries by Wigner, Professor Dyson, Mehta in the 60s, the breakthroughs of Harold Whittam and Craig Tracy produced a spark, which reignited the field. Their discoveries unleashed a great tide of energy and activity. And the field carries the marks of great science. Indeed, the field of random matrices begins to play a ubiquitous role in mathematics and physics. As a cherry on the ice cream, Harold Whittam was awarded the prestigious 2002 George Polya Prize together with Craig Tracy. I wish you, Harold, many more lives and hope to get together on September 24, 2012. Okay, some around in the early 80s. In the early 80s, 3 French mathematicians wrote down an interesting Hermitian matrix integral, a Gaussian Hermitian matrix integral with a, what is it, chalk actually? I mean, they wrote down a Hermitian matrix integral, Gaussian, but with a quartic perturbation in the exponential. Okay, thank you. And they showed, in fact, that this matrix has very interesting topological meanings. Now, namely, it counts ribbon graphs on Riemann surfaces. Then, about 10 years later, in the they actually also hinted that there might be a connection of that problem with tridiagonal matrices, and it's actually in the back you see the total lattice appearing. Then in the early 80s, Witten and Kontsevich wrote down another integral whose perturbative expansions has to do with the topology of the space of Riemann surfaces, marked Riemann surfaces, modalized space of marked Riemann surfaces. And they showed that this integral satisfies, in fact, Virasoro constraints. This integral that, in fact, Kontsevich wrote down was some kind of, matrix Airy function. And in fact, Mark Adler and I, this is joint work with Mark Adler, who is present here. We, in fact, started exploiting these ideas in the field of random matrices. So, in fact, I'm going to concentrate now on 2 integrals. Yes, I'm going to concentrate on 2 integrals, namely a first integral, which is an integral over an interval E, n-fold integral, delta nz to 2 beta, and this product here. Now, this shouldn't frighten you. This is just a formal sum of ti z k to the I. For instance, it includes, in particular, the Gaussian case, where you put, say, 2t equal to minus 1, and all those other ti is equal to 0. But you can do more clever things. You can say, well, let's put all the ti equal to minus 1 over I. And then you use this little formula, so you get 1 minus z to some power, if you like. So you can manufacture lots of integrals via this little trick. And then we will also consider rho is just some weight. We will also consider a second integral, which is an integral over the circle, taking n times delta n of z square, and this same kind of sum, this same kind of formal sum, but this time you have two sets of times which appear, t1, t2, and a second set of times s1, s2. Okay. In fact, it turns out that this integral is, as we all know, that is equal to the integral of the unitary group of this determinant to the power gamma times this function of traces dn. Okay. Now, what I'd like to discuss is the relation of these two integrals to integrable systems, firstly, and secondly, I like to see what the impact is of studying those two integrals onto combinatorics and probability. And in fact, indeed, this integral has a lot of applications. In various fields. I will just indicate a few. And in fact, all these fields will be discussed during this meeting. It has to do with the spectrum of random matrices, of course. It has to do, they can be related to integrals. Special cases can be related to integrals for groups, symmetric space, etc. They relate to statistics of the length along with increasing subsequences for random permutation, random words, random evolution, etc. And then they also have to do with multivariate statistics. I will say something about it. In particular, they have to do with the problem of testing the independence of two normal populations. And then finally, they also relate to non-intersecting random walks and Brownian motions. Okay? So, Mark and I, we try to understand what are the integral systems which are behind those two reasonably simple integrals, and also, what are these Virasoro constraints? What are the Virasoro constraints for those problems? And in fact, we started exploring that in a rather systematic way, and in this way we found, again, we reproved some noun results, among others by Harold Widom and Craig Tracy, but we also found a number of new facts. And so the first observation, and in fact, let me start with this integral now. The first observation is that under some suitable conditions on rho, I mean, you assume that the logarithmic derivative of rho, this is the same integral, that the logarithmic derivative of rho is a rational function. E can be just a disjoint union of intervals. Then you show that this integral satisfies Virasoro constraints in the following sense. This is a differential operator which depends on the endpoints, on the boundary points of E. This f is the denominator of that logarithmic derivative of rho. And then this is the Virasoro part. They are linear differential operators in T1, T2, etc. of at most second order. And this is the Heisenberg part. This forms the Heisenberg algebra. I will write down in a moment those relations. This is the Heisenberg algebra. And in fact, those generators, they form the following algebra, namely the commutator of jk and jl is given by k minus l jk plus l2, exactly like you would take the algebra formed by z to the k plus 1 ddz, exactly the same, except that now there's an extra piece, and this is called this central extension, There's an extra piece which only appears when k is equal to minus L. And that C, that number C, is what physicists call the central charge, which in fact can be computed. It's a nice formula in terms of the power which appears in the integral here. Okay? So for instance, for beta equal to 1, which is the easiest case, this would be equal to, the central charge would be equal to 1. Note that there's an interesting duality. Namely, if you replace beta by 1 over beta, you find the same value C. Okay? And that's a duality which, in fact, you all know, I mean, in other contexts. Now, what is the proof of that fact? I would say it's very simple. All you do, you replace, in this integral, you replace zk by zk plus epsilon f of zk to the n plus 1. Okay? So if you make a change of variables inside in the integrand, that will not change the value of the integral. So therefore, if you take the derivative of the result so obtained with regard to epsilon, that must be equal to 0. And then if you work a little bit, you will see exactly those things appearing here. I could show you what these things look like. I don't know whether it's terribly... but you will see it in some special cases. I don't think it's terribly illuminating, except that I think it's interesting to know that it satisfies the case of Virasoro, which satisfies that relation, and JK1 is a Heisenberg, which satisfies that relation.
F?
Sorry?
What's F in that little f?
That little f is the denominator of the logarithmic derivative of rho. I mean, that you have, if you do the computation. I mean, it's interesting to just do it for a one-fold integral. And already you can compute, you get those Virasoro constraints. Of course, if you do, you can do this kind of, you can apply this kind of technique also to the case of, say, Fredholm determinants, but then such an explicit thing will not work. But unfortunately, this is part of a much broader theory, which is called vertex operators, and which enable you to compute very, very quickly these kind of results. If you do this by hand, I assure you it will take you some time. It's very tedious. In fact, in the appendix of one of the papers, Mark, we have done the calculation really by hand. And so just to...
You assume G and F are polynomials.
I beg your pardon?
You assume G and F.
Yes, you will assume G and F. Of course, at this level, it's still all formal. You could just take entire functions, but in all the applications, they are indeed polynomials. So that's the first ingredient, is that those integrals satisfy those Virasoro constraints, whatever be beta. Okay. Now a second ingredient, which in a sense is almost by now is almost classical, is that those integrals, at least for special values of beta, satisfies certain integrable systems. So I wrote down here all I'm going to tell you here, you probably know very well. I wrote down the integral again there, and that is equal to the first observation. That's equal to a determinant of a moment matrix. A determinant of a moment matrix whose entries are the following moments. I should have written Zi, Zj is equal to this thing here. It's a Hankel matrix. And of course, we also know that for beta equal to 1, this can be written as the integral over Hermitian matrices, n times m Hermitian matrices, in the following way. Now, these moments with regard to this measure here, e to the minus v of z, I mean, this row, the row which I wrote down, I just write it as e to the minus v of z. I mean, this is a moment matrix with regard to this measure here. Now, it's a very easy little computation to take the partial derivative of each one of those moments with regard to tk, because that brings down a z to the k, in which case you get the integral of z to the I plus j plus k, so which I wrote down in the following way. So it's a very simple little thing, which you can then write down symbolically. You can write down symbolically as the partial derivative of M infinity, that is to say the semi-infinite matrix of moments, with regard to Tk, is a shift matrix k times M infinity. So they're just the same thing. Okay? And you know, so I'm just now showing you sort of a very general philosophy to generate the integral system from such determinants of such moments. And so what you do, the next step is that you consider a Borel decomposition of M infinity. That's to say, you take this semi-infinite matrix, you write it down as a product of a lower triangular matrix times an upper triangular matrix. That I put to the -1, that's irrelevant, really. So then in the end, the formulas come out right. But so you can always decompose, I mean, mostly, of course, generically, you can decompose as a product of a lower triangular matrix times an upper triangular matrix. I mean, whoever does such a thing knows that it is really it is equivalent to searching for orthogonal polynomials. This procedure is just tantamount to searching for orthogonal polynomials. And indeed, so you write down, so this matrix, so this matrix S, if you, of course, which depends on, I mean, this T means T1, T2, T3, etc. If you hit if you hit this vector 1z, z squared, etc. by S, you will find just a whole sequence of orthogonal polynomials. So they satisfy this perpendicular relation, and that's just the same thing. Then you dress up this shift lambda. I mean, this shift lambda, as I said before, this is equal to 0, 1, 0, 1, etc., 0 everywhere else. You dress this up with this matrix S. Then you find, it's again a neat little exercise, you find a symmetric tridiagonal matrix, which of course defines for you the three-step relations between those orthogonal polynomials. So this is in a way all classical. So what does one want to do now? We know that you have those very simple differential equations, in a way very, very elementary differential equations. You now wish to see what these differential equations imply on S, and so therefore on P, and so therefore on L. So that's really the next step. Okay. And that is so that is really what one finds, is that we had those differential equations on the other level of M infinity, which gives you a differential equation at the level of S. You can compute all that, and finally on L, and these are the differential equation, namely the partial derivative of L with regard to Ti is equal to a commutator of the projection of Li onto the Borel part. That is to say, take the lower triangular part, but do it intelligently, namely in such a way that in the decomposition dl infinity equal to Borel plus Q. So this lower triangular plus this Q part. Okay. So, and this is in fact the well-known total lattice. Of course, the total lattice was originally something which was finite. There are particles which were, say, on a circle and which were connected with nonlinear springs. But now this is in fact a semi-infinite problem. I don't know really what the interpretation is in terms of particles here. But it turns out that this simple integral that we had at the beginning leads, I mean, very naturally to the following integrable system. Now, once you have that, I mean, then there's a whole theory which was developed, the so-called theory of tau functions. You then show that the determinant of Mn satisfies, in fact, the following equation, which is called the KP, the Kadamp-Cespedes-Giashvili equation. It is the first equation in the whole hierarchy. I mean, you can show that they satisfy. I didn't write down the whole hierarchy because for the problem that we'll discuss, is that the only thing which will be useful. So you find this KP equation for this determinant, and I call them on purpose. They are called tau functions. Okay. Now, you will, of course, wonder what you do for other values of beta. We can do similar things for beta equal to 1/2 and 2, and we don't know what really happens for other betas. So that's and this is again, the slide that I will show you is somewhat of a repeat of things which are very, very familiar to many of you. So this was the original integral. This IN was the original integral, and now we know from the classic work of Meta and Dice, etc., that this is equal to the Pfaffian of a certain moment matrix Mn, and we also know that this integral up there, I mean, it's Mn and 2n. There's in the case of beta 1/2, it's an n by n matrix. In case equal to 2, you have to take a 2n by 2n matrix. Okay. It is equal to the integral over the symmetric matrices of that integrand, real symmetric matrices, and it is equal to the integral over the self-dual Hermitian quaternionic n by n matrices in the case beta equal to 2. Okay. So the M infinity is that matrix Mn is in fact so we are just following the same pattern as before. I mean, just exactly the same kind of thing. This matrix of Mn is a matrix of moments, and the moments are given by that little formula there, for some appropriate rho tilde, which is it's some square root of rho, but never mind, it's very closely related to rho, and it is for alpha equal to -1 corresponding to beta equal to 1/2, and alpha equal to 1 corresponding to beta equal to 2. I mean, this is in fact the derivative of the delta function. So in one case it will be a step function, and in the other case. And then one shows, having this formula, this is in fact skew symmetric, because if you flip around I and j, you will see that it's a little unfortunate. This sum is of the i's. It has nothing to do with I and j. Now, if you take the derivative, I would think this is skew symmetric. That's why if you flip around I and j, you just flip the sign. Now, as we did here, the partial derivative of this moment with regard to tk brings down yk plus z to the k, okay? Which in fact says that the partial derivative to tk is equal to yi plus k zj plus yi zj plus k. So which means the following relation, again with that shift and the shift transpose. That little differential equation for M infinity. In fact, it's an easy differential equation whose solution we know. I mean, at least some solution we know. And then you do more or less the same as before with some modifications, namely this Borel decomposition, which we did here. It cannot be done as such because we are talking about a skew-symmetric matrix, but you can do it upon putting in the middle a anti-symmetric matrix like this. Okay, so you find an S matrix which is a lower, and this is an upper triangular matrix which has which you can normalize things in such a way it has a special shape along the boundary. But let me not go into those details. And then you write down S of t of the vector 1 z squared, etc., and that produces for you skew orthogonal polynomials. Okay, so that is to say that those polynomials are perpendicular to themselves, but the inner product of Pn with Pn plus 1 is going to be plus 1. So the inner product of Pn and Pn will be given by this matrix here. Then, having this S, you then form this L matrix, of which those polynomials, I mean Lp is equal to Zp, and then you have those differential equations, try to see what these differential equations imply on S and on P and finally on L. And that's what I'm going to show you in the next slide. So again, following the same pattern as before, you find here that you find for L, a certain the partial derivative of L regards to Ti gives you a certain commutator. But this time, it's not a projection onto, it's not taking just the lower triangular part in this decomposition here, but it's taking a lower triangular part into a different decomposition, namely the decomposition of GL infinity to K plus SP infinity. Okay, so this is a totally different beast. I mean, this projection to K, and this is what we call the Pfaff lattice. Now, again, in this case, once we have such an integrable lattice, I mean, by all these lattices, the total lattice of Pfaff lattice, they all have an infinite number of integrals of the motion, which are basically given by traces of the powers of L. And then one has a well-established theory, which again has to be adapted quite severely in this case, namely that the Pfaffians of those moments, n times n matrix of moments, satisfies the following equation. So it is the same equation as before. It's the same equation as before, except for an additional piece. An additional piece, which is tau n minus 2 tau n plus 2 divided by tau n squared. Okay, that's the additional piece which you find. Now, remember that this is all a discussion of that first integral. You know, we had in the beginning. I promised you I would discuss two integrals. So this is this first integral. Now I like to say, maybe more sketchily, I will discuss the second integral. And the second integral, again, one looks for Virasoro constraints, and then one looks for an associated integral system. So here we have our same integral, and it satisfies Virasoro constraints. This time, before, it satisfies a whole subalgebra, an infinite subalgebra of Virasoro constraints. This time, it's a tiny subalgebra of Virasoro constraints. Namely, it satisfies those. It satisfies Vk of this integral is equal to 0 for those generators v minus 1, v0, and v1, and that's it. It stops there. Before we had v minus 1, v0, v1, v2, etc. all the way. So it's a much more, but enough that you can do things with it. So these are. In fact, here you see, I said to you that they are differential operators. Here you see them in the flesh. Okay? They are fairly easy things. And so the second concern was to find an integral system related to those integrals, and I will do that very sketchily because it follows more or less the same method as before. So again we have our integral. You form moments defined in the following way, defined on S1, the circle S1. Those moments, again, very elemental computation. If you take the derivative of this moment regard to tk, it brings down a 0 to k, so it gives you this little equation. And the derivative of this moment regard to sk brings down a minus e to minus k, and that gives you this little equation. Okay. So before we had one equation, at some point we had, and now we have two equations in the t case, t1, t2, t3, etc., s1, s2, s3, etc. And then you form, from this is a Toeplitz matrix, you form the following decomposition, s minus 1, s2, and you form in this way biorthogonal polynomials by hitting 1 zz squared by s1 and s2 transpose minus 1. They are biorthogonal in that sense. The Hn is some normalizing factor, they are not monic. And then there's then as before, we dress up the shift, but now we have, in this case, we have two matrices, lower triangular, and S2 is an upper triangular matrix. So we dress up L1 we dress up lambda, and lambda minus 1, or lambda transpose. And that gives you two matrices, which in fact have a very peculiar form. Namely, they try to be rank 2. They are not rank 2, they try to be rank 2, because all the entries are products of xi times yj. Okay? So these are the two matrices. And what are those variables here? What are those variables here? Those variables, in fact, are the bi-orthogonal polynomials evaluated at z equal to 0. That means it's the zeros order term of the orthogonal polynomial. Oh yeah, no, sorry, it's right here. So those xn's, those variables here, they're in fact ratios of those integrals. I wrote down, just as a reminder, I wrote down what those integrals are. This is in plus is the integral of the unitary group of determinant of m. In minus is the integral determinant of to the minus 1 of that same integrand. Okay, I mean, in is just the thing with 0 here, but this does not appear. So these things, these xn's are equal to this. That is the value of the integral at z equal to 0, of the second set of integral of polynomials, orthogonal polynomials z equal to 0, and is equal to the ratio of these integrals. And they satisfy, since we have that the m infinity, which was the established matrix of moment, satisfies some two sets of differential equations. We can now we can see what it induces at the level of the S1 and S2, and so therefore we can see what it induces on the level of L1 and L2. And that's in fact a lattice which in fact has been very much studied, certainly in the 80s, by the Kyoto School of Tau functions. It has been studied, and it's called the two-dimensional total lattice. So this means the DLI dTn is equal to the upper triangular part of L1 to the n commuted with Li, and this is the lower triangular part commuted with Li. But what is new, what is interesting, is that these equations, they actually preserve the form of the L1, L2. If you start flowing according to those equations, the x and y i's, the L1, L2 will have the same form. And with regard to the x and the y i's, they are a genuine Hamiltonian system, which one can write down, which is completely integrable in the sense that it has an infinite set of integrals of the motion. Now, let's look at this is now a lot of machinery which may only be of interest to the integral community, but you can actually do things with it. Namely, I said in the very beginning, if you take this integral and now you put in special values of those TIs here. You take that integral, and now you take special value of TIs, which I wrote down here. I mean, it doesn't really matter, but I will show you what the result is. The result is then you produce the following kind of integral. You produce the following kind of integral, namely the integral of un of the trace of p1m plus p2m bar, determinant of m gamma plus epsilon times those two products, just by picking special values of ti and si. And then this is equal to this integral over S1, and of course is also equal to a tupless determinant, and where the rho is the following weight. So P1 and P2 are polynomials, just arbitrary polynomials. It turns out, for what I will do, the degree should differ by at most 1. And then one shows, in fact, a new phenomenon, namely that if you look at those variables xn, which I wrote down here, I mean exactly the same xn and yn, they satisfy inductive rational n1 plus 2 plus 4 step relations. That is to say that depending. So n1 is the degree of p1, and 2 is the degree of p2. Okay, and then xn and yn's can be expressed in terms as rational functions in terms of these things here. For instance, if n1 and if n1 and 2 is degree 1, then you will find three-step relations. And in fact, this whole this result was actually very much inspired by a visit in Boston of Alexei Borodin. In fact, he had found in a case which I will show in a moment, very interesting three-step relations, which in fact was known under the name of Macmillan's equations. So, but let me just continue here for a second. So these ratios, those ratios are, in fact, you can generate them all in a rational way. If you know x1, y1, a few of them in the beginning, all the other ones can be generated in a rational way. And in addition, that implies that the INs, the integrals themselves, in fact, can be written in a rational way in terms of those xi and yi's in a fine way. So basically, all you have to know is the values of the integrals in the beginning for I1, I2, I mean for a one-fold, two-fold, three-fold integral, and then you can do everything in a rational way. I would say the people interested in these things. I mean, those maps, x and y, the rational map they satisfy is something which is called the singularity confinement property. That is to say that the generic solution will, with regard to n, when you go on, the generic solution will at some point blow up, and then immediately after will be finite again. Okay, and that's in fact something is the analog, is a discrete analog of something that's called the Pain-Levé property for continuous differential equations. So now you might just, since I have introduced all this machinery before, maybe I should say something on how this is obtained. Well, it's actually obtained in a rather in a rather easy way, namely. So the nature of those rational relations here, they are as follows. You consider those Virasoro constraints. Okay, I'm not going to go to all the formulas again, but just take a certain, you know it's zero. You know that those integrals satisfy the Virasoro constraints. You know it's automatically zero. You choose appropriate A, B, and C, I mean, which has to do with that special locus of Ti and Si that I consider. And then this is equal to a difference in N of a certain sum of alpha in L1, that matrix which try to be which try to have rank 2. Remember that matrix of xi, yj, minus the sum of bin. There's no t. The t should be there. L2 to the I plus something like that. That's the, so that expression which is 0 is equal to this, and that's precisely the nature. It's those rational relations are very, very easy expressible in terms of those matrices L1 and L2. That's really what I want to say. You find a second relation also by a similar trick, which I don't want to go. You take the dt1 of that relation, and you find a similar thing. Okay. Now let's go to an example which we all love, and which really I think most people in this community know very well. Namely, let's take the very special case. Remember, we always are talking about this integral there. And now let's take the very special case. You put all the Sj, Tj equal to 0, except T1, S1 equal to square root of T. And then we know that that this generates this unusual generating function for that for the probability that the length, the longest strictly including sequence of that permutation. I mean, the Sk is the permutation group, the permutation for 1 up to k. Now you look at the increasing subsequence of pk, you look at the length, the long and strictly increasing sequence of pk, which is Ulam's problem. You look at the probability, given that you have uniform probability on the permutation, you look at the probability that the length is smaller than n, and you form that generating function for k going from 0 to infinity. Then Gessel showed us that this was a tuplet determinant, and then Eric Rines showed that this, of course, is an integral of the unitary group. Now, it was shown by Harold Whitham, Craig Tracy, that this, in fact, is the exponential, the integral from 0 to t, the log of t over u, v and u du, where Vn, as you'll see in the next slide, in fact, is a solution of Panevet-5 equation with a certain initial condition. We actually, via these Virasoro methods, we actually reproved this result in a very quick way. But there's one extra fact now, is that if you look at those xn's andyn's, which are the entries of that matrix L1 and L2, which I showed you about 2 slides ago, which in this case is the ratio of those two integrals, and which is also, as I mentioned, the orthogonal polynomial at z equal to 0, that those xn's they satisfy rational relations, which I will show you in the next slide. And so Alexei Borodin then showed that those xn's satisfy the following beautiful little equation, okay, which in fact he pointed out is a discrete version of Panevet-2. So we have, in fact, yes, and also I wrote down here, these are the xn's, and if you form Vn equal to 1 minus xn squared, you could just take xn squared itself. I mean, that satisfies this Panevet-5 equation. That satisfies this Panevet-5 equation with some very peculiar initial condition. So there's an interesting phenomenon here, is that you have two things. First of all, you have that these kind of integral, this combinatorics here, is expressed in terms of some Panevet-5 equation solution Vn. And the second thing is that those xn's, that they satisfy this rational relation. So if you know x1 and x2, you know everything all the way in a rational way. So this is a feature which you find in all those problems. Now, yes. For instance, I could show you again, maybe I'm not going to spend too much time on that, but I can show you another situation, which in fact was also initiated by Craig Tracy and Howard Whitham. You look at the same situation. So you look at define weight 1 plus z, the alpha e to minus s e to minus 1. This is obtained from this integral, which I wrote down, maybe it's still, no, it's not here, which I wrote down. You take all the iti equal to this and all the si equal to 0 except for s1 equal to s. And then this has to do with the words pk of length k from an alphabet of alpha letters. You look at this probability. Again, you have uniform probability on those permutations. You form this generating function here. Then that is equal to, that was shown by Tracy and Whitham, this is equal to the integral of the unitary group of determined I plus n to the alpha e to minus s. And it was then shown that it is equal to the following exponential, where hn is a solution, again, of the Panevet-5 equation. Again, we reproved that via using the Virasoro methods. But then there's an extra ingredient now, is that those xn's and yn's, those ratios of integral, xn goes with +1, yn goes with -1. We always have that those integrals in, in fact, this in is given in terms of this xi, yi by this little formula, the formula which we have seen a number of times. I mean, that satisfies that again satisfies the x and y ends satisfy a 3-step and 4-step relation, which is written here. Of course, this is very clumsy, it's complicated, but if you write it down in terms of this L1 and L2 matrix, it's a very easy little thing, but this is written out. So the xn plus 1 and yn plus 1 can be expressed rationally in terms of xn, yn, xn minus 1, yn minus 1, and some initial condition. So you can solve inductively in this way all the xn and the yns. So again, in this instance, you see again that phenomenon. You have on the one hand, you have certain quantity satisfy this Penrose 5 equation, and on the other hand, you have this this phenomenon of a rational relation for those integrals. Now, I like to discuss another kind of integral. So this is going to be example 3 here. We were led actually at looking at the following kind of integral. You consider the integral from 0 to 1, p-fold integral from 0 to 1 of the following kind of thing here, where beta is equal to 1, 1/2, or 2. And it turns out that this integral, with those precise p and q's and n, is equal to an integral over the Grassmannian of p-planes into Cn, Rn, or Hn, H being the quaternions. Okay? So this is equal to that integral of the Grassmannian, which in fact that Grassmannian is known to be a quotient of a group via a subgroup, G over K. And this is the exponential of x. The trace of I plus z, well, is the transpose, and well, in the case it's different in of course C, R, and H. Minus 1 determines this. And this Z is a n minus p times p matrix. They are not square matrices. It's n minus p times p matrix. It is a certain, I don't want to go into that now, but it's a certain parametrization of the Grassmannian of p plane into Cn, or Rn, or Hn. Now, it turns out that this integral has 2 interesting features, and in fact, which I really would like to show, because I don't understand the connection between those features. But by looking at the work of the statisticians James and Constantine in the 50s, 60s, we found that there's also in the 80s, Muirhead, statistician, wrote a book on the subject. We found that in fact this distribution here, I mean this is in some sense the Laplace transform of a certain distribution. And that distribution has to do with measuring, or rather testing, the independence of 2 Gaussian populations. So you take 2 Gaussian populations, x1 up to xp, 1 up to yq, centered at 0, and this is the covariance matrix. Now, Hotelling, already in the 30s, showed that there is a linear transformation of the x's and the y's in such a way that this sigma can be brought in a rather easy fashion, where P is a diagonal matrix, rho 1 up to rho P, which I call the canonical correlation coefficients. They are, in fact, the zeros of a certain, a certain characteristic polynomial. Yeah, the zeros, the following, let's see, yeah, the other, where is it? Yes, the zeros, in fact, the roots of this determinant, where the sigma 1, 1, sigma 1, 2, so 2, 2 are the, gives you the covariance matrix. Now, what do you do if you want to test the independence of 2 known populations? You will try to find samples. You will then form a sample covariance matrix, which is formed the following way. You take, these are your n large than p plus q samples here. You then form a matrix of these samples, and then the estimators, Ri, for these canonical correlation coefficients, rho I, are given by the rules of the following matrix. Or the rule by the following characteristic polynomial, where this S, this is S11, just you look at your measurement, you look at XX transpose, XY transpose, etc. This is S11, this is S22, this is S12, S21. So you form the following, this is called the sample covariance matrix, and these Ri are the maximum likelihood estimators for these rows. And in fact, James and Constantine, via, interestingly enough, they use the whole theory of Grassmannians. They show, in fact, that the square of those estimators satisfy a certain probability distribution whose density is given here. And that's exactly the distribution that we had at the beginning. So where we take here the Laplace transform that distribution. Okay. Now, that's one fact which is, it's one thing. Now, there's another thing. Now, if you expand this in terms of x, because let me go back for 1 second to my original. If you expand this integral here with regard to x, then you find some interesting things. But let me do that. It's easier to explain, it gets a bit more tricky, but it's easier to explain when p equal to q. That is to say, when your two populations are same size. Then you get the following. You get the following is that so here we have again the, let me put this on this side. So that's its integral. I put p equal to q, so that means that term sort of goes out. It gets quite a bit simpler. You get this. And let me take the case where you have c here, so not r and h. If you have c here, then this is equal to, again, one has some sort of formula which expresses in terms of a solution of the span of a 5 equation. This u here, this u of y is a solution of the span of a 5 equation with a peculiar initial condition. It's a very special span of a 5 equation. But then there's another fact. If you expand this in terms of x, okay, if you expand this in terms of x, you actually find some interesting combinatorics. And I'd like to just for 1 second explain what it is. It looks not at longest increasing sequence, but at some other thing. So this probability here, which I wrote down, let me explain what it really is. This probability is a probability on random words. That is to say, you have random words of length k taken from an alphabet 1, 2 up to p. Okay? And so as I say, there can be repetitions. And you now look at the words in such a way that the longest decreasing sequence of p of pi is equal to p. So that means to say that in the word that you pick, there has to be p has to appear, and then a little later p minus 1 has to appear, still a little later p minus 2, etc., up to 1. Okay? So that means that all the letters of the alphabet have to appear, but somehow in some decreasing order. And then you say that the. Now let's look at IP. Now IP is the length, the longest increasing sequence if you're allowed to take blocks. You take blocks, you subdivide your permutation in blocks. You look at the longest increasing sequence in each block, and then you take the sum of those lengths. Okay, so that means that that length for IP, if I take p blocks, well, what will I do? I will take all the p's, and then all the p minus 1s, all the p minus 2, all the 2, and the 1s. Clearly, the length, the longest increasing sequence in that case, by taking the sum of those lengths, all those blocks, would be equal to k. That's a trivial thing. But this is now this is non-trivial. So I consider this permutation. I subdivide in p minus 1 blocks. Okay, I look at the length of the longest increasing sequence within each block, and I take the sum of all those guys. Okay, now I say that this has to be smaller than k minus n minus p. So this statistical integral here that measures actually the following combinatorics. So I don't know why that's the case, but it is the case. Now, in the remaining maybe 5 minutes, I like to give actually another application of Virasoro in a very different context. In recent work we have, Mark and I have done, and here I will be very sketchy. So that is maybe example number 4 or something like that. So I consider random walks, but you'll see random walks in a moment. There are no random walks yet. So let's consider this is the integral which you have seen many times appearing during this hour. You take the integral of the unitary group of that integrand. Now let me consider shifts. So I shift t1 into 1 plus z, s1 in s1 minus z. And that leads to the following integral. Okay. Now let me expand this into a Fourier expansion in sure polynomials. I mean, that can always be done. I mean, this integral can be expanded into this sum. Okay. So you have a lambda of mu. There are numbers which will depend on z and functions of z. These are the sure polynomials correspond to the partition lambda. Sure polynomials to the partition mu. Because the nature of that integral, the length of the first column, those partitions have to be in between 0 and n. So the length of the first column has to be smaller than n for lambda 1 and mu 1. So this is really Fourier expansion. And of course, it's clear that if you put t and s equal to 0, you find the Gessel-Reins integral here, which we discussed before, which led to all these combinatorics, which is equal to, in fact, certain tuplets determinant, and which can be written in terms of Bessel functions. So let me see, easy u plus u minus 1 is the sum. Well, this is not exactly Bessel function, because there's some I missing there, but up to that I, it's going to be Bessel functions. Now, I like to understand the nature of a lambda mu of z here, of those coefficients. That's what I want to understand. And I will show you a big slide, which of course contains lots of things, but let me just very sketchily discuss that. It's a big slide. So there are lots of formulas there. So this a lambda mu of z, these coefficients here, those coefficients here, they are in fact equal to the integral of that, I mean, this matrix integral, so to speak, where this is s lambda, again, are sure polynomials, which can be expressed, and that's essentially Cauchy-Binet formula, which can be expressed in terms of determinants of e to the z u plus u minus 1, the coefficient of u to the yi minus xj. Okay? So that's really, this integral can be expressed in that way. Or a determinant can be expanded in that fashion. Okay? Right. So now we now have. I should point out an easy little thing is that if you look at the. No, I'm looking at something. There's an eraser here. So if you look at the number of walks of k steps from x1, xn to y1 to yn, assuming that your walk, so we are walking Zn, it's a walk in Zn. We assume that you can only walk plus or minus E1 or plus or minus E2, etc. So you can go up and down or left and right. These are the only steps you can make. Now this is equal to that. That's a very classical form. It's equal to the sum of ui plus ui minus 1. This is the case power 1 to n. And then you take the coefficient of u, the yi minus xi, u n yn minus xn here, yn minus xn. So that's a very classical thing, is that in order to find the number of walks, you look, it's related to the combinatorics of this. Okay. Now there's an old principle by Desiré-André, dating the 19th century, which tells you what you do if you have a boundary, which in fact, if you take steps, random walks which stay within say z1, z2, this chamber z1 to zn. You look at this chamber and you look at walks which so it is in fact given by a certain reflection principle. So that's exactly what I wrote down here. That's exactly the content of that formula here. This is equal to the sum, the generating function of the number of walks of k steps from x1, xn up to y1 up to yn zn within this cell u1 bigger than un. Okay. So using that Desiré-André, so which can also be translated into non-intersecting walks in Z now. I mean, in Z, going in k steps from x1 to xn to y1 to yn. So, in fact, that integral, that integral, if you expand in Z, that actually gives you certain numbers which are, yeah, I should really say that the x and the y are related to the partition lambda and mu in the following way. But of course, they are very peculiar walks. They are very peculiar walks which some of you certainly know very well. They are lockstep walks, which are as follows. I just gave an example here. That is to say that for each step you can only only one walk is walking. At the second step, only one walk is walking, etc. So they all, one is walking, all the other one stay put, etc. Up to the very end. Now, if you apply the Virasoro to this, and then you find the following. You can apply Virasoro. You know that the original integral actually satisfies. You know that the original integral, in fact, satisfies Virasoro constraints, and we had this integral here, which was the sum. We had a certain integral, which was equal to the sum of a lambda mu of z, s lambda of t, s mu of minus s. So we had, now if you apply the Virasoro constraint to this, and that means that you have to understand what the Virasoro constraint do to s lambda s mu. If you do that, I mean, then you find, in fact, certain difference relations for those b's, which you then can write down in the following fashion. And that will be almost the last slide I will show. So it gives you the following result, is that the probability that n random walks in Z starting from x to y, reach y from x to y in k steps, conditioned by the fact that they do not intersect, that probability, in fact, satisfies discrete Dyson diffusion. Because I will need to explain to you what Professor Dyson did so many years ago on that. But it satisfies a certain, this pkxy satisfies a certain equation where Lx and Ly is the following thing. This is the Van der Monde determinant related to x1, x2, etc., the initial condition. So this is the Van der Monde determinant related to the final. You have to get to y1, y2, yn, etc. These are just little difference operators in the yi. Delta xi of x of yi is equal to f of x plus ei y minus f of xy. Okay. Now you let the steps k go to infinity. N stays put. You let k go to infinity. Okay. And then in fact you show that these equations, they actually tend to the following equation, and this is now really the last slide. they in fact tend to the following diffusion. So if you take this equation here, you now rescale things properly, replace xi by xi, divide by square root of k, etc. So you take the initial points, you let them go to infinity. The spacing becomes larger and larger. The number of steps also becomes larger and larger in a certain, in the right way. I mean, then in fact it will tend. I mean, that equation then can be expanded in k. In fact, can be expanded in 1 over the square root of k, and you find the following equation here, which of course must be 0. This is 0, so that must be 0 in the limit. This is some trivial factor which in fact is automatically 0, but you get this. You get this, and these are exactly the. I wrote down here that this is exactly the Dyson diffusion, namely that. No, it's really. So, what did Professor Dyson do many years ago? He showed that the probability that n Brownian motion r starting from x reach y plus dy at time t, given that they do not intersect, is given by this transition probability, and that satisfies, in fact, there's a forward and a backwards equation. Forward equation means that you look at the differential equation with regard to the final points. Backwards equation means that you look at the differential equation in the starting points. It satisfies the following. Where this is Laplacian, and this E of x, in fact, is the following kind of object. Okay. So it shows that these equations here are, in fact, the discrete version of the Dyson diffusion for this peculiar random walk, okay? And that, in fact, it tends to those things there. Thank you very much.
Well, we have time for a couple of short questions.
I have a remark.
Yes.
I think the picture, random walk picture is not right. I mean, they go ordinary random walk. That's one.
Sorry?
I mean, you have this picture.
You mean this one?
Yeah. They should all walk either left or right.
Yeah, they go all right and left, yes. In fact, they do on the picture.
The way you only indicate one move at a time. That's not what you like there.
No, no, because in Zn I allow in Zn I allow motions left.
The question should be what you really wrote down with the decay.
No, I mean in Zn I can move plus or minus E1, plus or minus E2, etc. Which means if you look at it from the point of view of this is just a random walk on Z. I mean then that means that only one walker can walk. Yes.
Well, let's thank the speaker again.